Hello and welcome to the channel. In this video, I'll discuss the black box definition of machine learning, how attention modules and feature engineering might assist the development of an efficient and interpretable AI system for facial detection that we might trust. My name is Ruslan, I'm the CTO. On this channel, I discuss AI-based application in an easier to understand way. As a geologist, geophysicist, we based our understanding and interpretation of the subsurface on underlying facts, reasons, and correlations. Most of the time, current AI/ML solutions for seismic facies analysis provide us with facies distribution as it is, without any reasoning. And suppose we cannot interpret the result or understand the logic of the proposed facies distribution. In that case, we cannot fully rely on it entirely. So, I want to cover a recently published paper that takes facies analysis to the next level and provide an interpretable AI solution which outperforms segmentation networks like SegNet and UNet. And we are starting right now. There is one point about machine learning solutions you need to be aware of. You might already know about it. Machine learning prediction is produced by code, but it's not code. For example, traditional software development is based on predefined scenarios with a chain of conditional statements. Scenarios can always be explained and results can be reproduced. On the other hand, the AI/ML development is based on statistical methods that learn directly from data. Scenarios can hardly be understood and results are probabilistic. That is why machine learning solutions are not interpretable out of the box. And given a large amount of data, a neural network can learn any function. An example from petroleum engineering, predicting the well performance within the field based on the data such as well location and skin factor. And because the neural network develops a relation by observing how data changes, the approximation might be arbitrarily complex. What is the contribution of a skin factor or location for the production? We can't extract answer from the given approximation, hence the neural network viewed as a black box solution, and there is no way to extract the function from it. A trained neural network is just a set of interconnected weights that adhere to a specific architecture. Machine learning solutions can undoubtedly be described as a black box, even though it might provide substantial benefit for the quality and efficiency of the work. We must grasp what is contributing to a solution in a high-stakes situation. For example, deciding where to drill a well in the presence of a subsurface uncertainty. Scientists have been creating interpretable and explainable machine learning models to better grasp the neural network's internal logic and be more confident in the prediction. Let's consider only computer vision problems for now. Explainable AI is the method that tries to explain the outcomes by highlighting a part of the image responsible for the final decision. This explanation can be applied to various neural networks to explain its output, but it doesn't tell much of a model itself. There is a paper that describes a lot of the different explainers for computer vision problem. The links are in the description. And the other is interpretable models. Here are the methods that can be explained based on their internal structure. We can also bring any deep learning model closer to interpretable by appending a neural network architecture with a prototyping layer proposed by Cynthia. Check out her video if you haven't already. Between explainable and interpretable machine learning models, I would choose interpretable models every time, because they offer us enough reasoning to determine whether the solution is appropriate. I'm not suggesting that every case requires an explanation. If it is simple manual work that is being automated with machine learning, I would argue that we don't need an interpretable or explainable model. In any case, some other high-stakes application would require it, and we need to work hard on it. Let's look at a publication that uses an attention-based deep dilated convolutional neural network for interpreting seismic facies. Although the authors talked about interpretable AI solution, the earlier definitions that I've talked already classifies this as an attempt to construct an explainable AI solution, not interpretable. They claim that while machine learning methods and deep learning networks improve the efficiency and accuracy of facies segmentation, They provide only limited interpretability for geoscientists. As a result, models do not offer novel insights into geology or geophysics. In the core, the paper proposed two improvements that helps to produce exceptional results. The combination of deep dilated convolutions and feature engineering based on several spectral components improves facial analysis accuracy and efficiency. Adding an attentional mechanism that maps the facial recognition to spectral properties helps in understanding the facies to geophysical data relationship. Let us take each point and discuss how they could improve the segmentation. And we start with dilated convolutions. Dilated convolutions inflate the kernel by inserting spaces between the kernel components. Dilated convolutions are used to enhance the receptive field of output units without increasing the kernel size. Then let's talk about feature engineering. The authors use spectral decomposition attribute to enhance the hidden geological information. The spectral decomposition, as we know, aids in stratigraphic interpretation by boosting thin bed resolution and displaying bed thickness variability. To put it differently, different spectral response emphasizes geological formations at various scale. Additionally, because noise at different frequencies has varied strength, combining multispectral components can inherently enhance signal-to-noise ratio. The velvet transform is used in this article to implement spectral decomposition. They've selected spectral components at 10, 40 and 60 Hz. From my perspective and based on my experience, I usually don't like doing feature engineering for deep learning methods because of a universal approximation theorem, which states that a neural network may get as near to a function as needed given sufficient parameters. That means that you can let the neural network to figure out the feature extraction by itself and the mapping from input to the output. But I also understand the other side. If you have insights into the crucial qualities, you can give a neural network a break and do some of its job. In this case, why do we force the network to recognize that spectral decomposition is significant for facies analysis, when domain knowledge clearly states that it is? You may utilize fewer parameters and reduce the risk of overfitting. The next step is to explain how neural networks work by incorporating spatial attention modules in the architecture. The attention modules draw attention to relevant regions that are important for the prediction. Including such models in the facial segmentation architecture would allow observing attention maps that highlights the seismic image region, contributing to the facies segmentation task. Alright, let's see the results. The authors presented results for the Netherlands F3 3D seismic survey acquired in the North Sea. They compared the result of the proposed method with the state-of-the-art segmentation architectures like SegNet, UNet, and others by using intersection of a union as a metric. Here is the result that shows the inclusion of the proposed improvements into the process of determining facies results in better facies segmentation for nearly almost all the facies presented in F3 block seismic data. Furthermore, by showing spatial spectral attention maps, the resulting attention map can illustrate the geological interpretation. As always, for more details about the implementation, read the publication link in the description of this video. If you are interested in learning more, there is a video on my channel regarding the introduction to seismic facies analysis. Thanks for watching this video, see you next time.